Hi class, Dr. Searcy here with the video lecture for the Chapter 8 textbook. As you can see, the title of the chapter is Introduction to Hypothesis Testing. And you may have noticed over the past couple of chapters, I've been doing these reviews to open the chapter up with. I'm going to do that again this time, but the review I'm going to go over with you right now is over this term that we've been using since about chapter 1, descriptive statistics. The thing that I want you to remember is that back in chapter 1, I talked about how there are basically two types of statistics that you're going to learn in this class this semester. The first one was descriptive statistics. The second term was inferential statistics. And we're going to start learning about inferential statistics in this chapter. So before we do, I want to just remind you of everything that you've learned about with regard to descriptive statistics first. So let's remember some of the terms that we learned about descriptive statistics. One term is central tendency, and this is kind of like an umbrella term referring to three different types of measurement where we're looking to see how our data that we've collected congregates. So a first term that we've used with regard to central tendency is the mean, right? And we've talked about the mean as being defined either of these two ways, but in either case, you're finding the sum of the scores in your data and you're dividing that sum by the number of participants that you have. Just remember that all semester long, we've been referring to two different ways that you can calculate the mean, either calculating the population mean or calculating the sample mean. The difference between the two is that with the population, you're relying on population information. With the sample, you're relying on sample information. So then another term that we've been talking about with regard to central tendency is the median. And all you need to remember with this is that the median is the middle score of the data. Maybe another thing that you can remember is that of all the different formulas that we've been talking about, going all the way up to chapter 7, we really haven't used the median in any of those formulas, right? We haven't really used it as a measurement tool. Same thing you could say with the third type of measurement, the mode. And remember that we define that as the score that's observed the most inside of your data. Now, staying with this idea of reminding you about what descriptive statistics are, I also want to make sure that you remember that there's another term that we've been using all semester long, and that other term is variability. And there are different measures of variability that we can talk about as well. To begin with, just remember that we've been talking about variability as basically the distance that any raw score is away from the mean. So a first measure that we've used to talk about that is the range, right? So remember, the range is simply where you find the highest number, the highest score in your data, and you subtract the smallest number or the smallest score from it. And with that, then you get a sense of how much of a spread you have in terms of your data. From there, another term that we've talked about is variance. Here, I'm just going to offer the mathematical equations that express variance. First, we can say that we can calculate population variance, which is denoted by this lowercase sigma squared. And just remember that the formula for it is sum of squares over uppercase N. Hopefully, you remember at this point everything that you need to do to calculate sum of squares. And I'm thinking that you do because we've calculated it a lot this semester. So just remember that the other way that you can represent variance is with a sample variance. Here, the only difference is we'd say that you're still calculating the sum of squares, but instead of using a population N, you're using the degrees of freedom, right? And the degrees of freedom was the size of your sample, that lowercase n minus 1. But the important thing that we used variance to give us was a sense of what our standard deviation is with our data. Right, so remember the standard deviation is the standardized distance that the scores are taking away from the mean, how far they're getting away from the mean. And formulas that we've used to calculate this are now a lowercase sigma and a lowercase s. Remember, now all we're doing is we're taking our variance and we're finding the square root of it with both formulas. Okay, so now at this point, we can go ahead and start to introduce the new term that we're going to use this semester. And that new term is inferential statistics. Okay, so remember that we said that the purpose of the descriptive statistics was to help us summarize and organize the data, right? To help us see what it is that we have in terms of our scores. Now, once we've done that, we will use inferential statistics to answer other questions. Specifically, I want to just offer this definition of what we mean by this term statistics. We're saying that in inferential statistics, we're using a random sample of data taken from a population to describe and make inferences about the population. Right, so everything that we've already been talking about this so far this semester, we're just saying that we have some population that we want to make some comment about, but remember that we can't get to everyone in the population, so what we do is we recruit participants from the population, and we use those participants to produce a sample. Here in our definition of inferential statistics, we're saying that we're doing this with a specific purpose in mind. And that specific purpose is to make these inferences. What do we mean by inferences? Basically, we're saying that we want to make conclusions about the data, right? We want to be able to say some definitive things about the population. So we've recruited the sample participants from the population, and now we're saying that we're doing that so that we can turn right back around and make these inferences about this population that we're interested in. Okay, so that's what we're doing when we conduct inferential statistical analyses. Another thing that we could say is happening here is that we are attempting to test a theory, right? And the idea with this is we're saying that we want to make this inference, we want to make this conclusion about our population. We're doing that because we have some type of theory with regard to that population. And here, by the term theory, I'm just really referring to an explanation. We have some explanation that we have about some way that the population is behaving, right? And so we've got that theory, we've got this explanation, and we want to test it. So how do we test it? Well, we recruit participants, we expose them to these different facets of our theory, and then we look at their reaction, and based on what we see in the reaction, we make our inferences, not just about the sample, but about the population that that sample comes out of. Okay, so when I say that we want to test a theory, then what we're saying is that we're going to take that theory and we're going to use it to form what we refer to as a hypothesis. What do we mean by this term hypothesis? Basically, we're saying that we're taking our theory and we're boiling it down. We're taking it from like this general statement of how things work to now a specific statement about how things work. And here basically the difference is this is how it's going to work in the world. This is how it would work under our control. If we controlled everything that we had to do with the population and the theory, and we said that we could make things happen according to what the theory says, then we would predict a specific outcome. Right, that's our hypothesis. What kind of study is it that a researcher will do this, will come up with a theory and then a hypothesis they can test? Well, the type of study that they're going to do this with is an experiment, right? So they've developed a theory about some way that a population behaves. They want to test that theory. So they come up with some testable statement, and then they test that statement inside of an experiment. Now remember, we've kind of talked about how experiments work at the beginning of the semester, so I'll just remind you some of the more important points that are happening here. One thing that we're saying that is happening is the researcher is doing something to the participant. Now remember, we refer to this as the IV, the independent variable, the thing that the researcher does. Here, I've just got a generic way that we could say that this is happening. We could say that the researcher is going to administer some type of treatment to a group of participants. One running example of an experiment that we've been talking about all semester long is having some people who are experiencing depression, and a researcher gives them some type of new drug to see if the drug will have any effect on the level of depression. That would be this example where a researcher is administering some type of treatment. That administration of the treatment is referred to as the independent variable. Now, one of the things that you want to remember here is that the researcher is administering the treatment with the goal of determining whether the treatment is effective or not. Right? So after the treatment has been administered, the researcher is going to continue to observe the participants to get some kind of data out of them to see, well, what's the effect of the treatment, right? And so we talked about that part of an experiment as well, and we said that that's this then part, where now we're looking to see if the participant is having the reaction that we predicted. Specifically, is the treatment that we administered to the participant, is it effective in the way that we predicted it was going to be effective? So, for example, if a researcher gave some depressed individuals some antidepressant, did the antidepressant have any effect on the depressed individuals? Was there some kind of noticeable, detectable difference in the level of depression that these people were expressing? So the other thing that you want to remember is that whereas we called this administration of the treatment the IV, we also refer to the measurement of the effectiveness as the DV, right? So independent variable is being administered, and then we are measuring the dependent variable. We're measuring the participant's reaction. Okay, so when we use inferential statistics, we're using inferential statistics to help us answer this question. Was the treatment effective or was it not effective? Okay, so from there, the next thing that you want to understand is that this is going to happen in terms of a process. And that process is referred to as hypothesis testing. Here, I'm noting that the process that we're talking about is a 4-step process, right? So there's 4 steps that a researcher is going to conduct as they are figuring out the answer to their question. To begin with, let's just remember the purpose of the hypothesis test is to answer this question. Was the independent variable effective? Did it do the thing that the researcher was predicting it would do? Okay, so let's take a look at the 4-step process that happens here. We could say that the first step is that a researcher is going to make a statement. Maybe to help us understand what we're saying here is the researcher is going to state something. what are they going to state? They're going to state their prediction. Since we've used a more formal term for this, let's just note this is where they're going to also state their hypothesis. Okay? So they're stating what they're predicting is going to happen as a result of their treatment that they're administering. Now, when the researcher makes this statement, the researcher generally makes it in two parts. And so I'll describe one part at a time. The first part that we can talk about is this part called the null hypothesis, right? So we're saying that they're making this hypothesis, this prediction. If we're talking about the null hypothesis, basically what we're saying here is that the researcher is predicting that the IV is not effective, right? The thing that we did to our participants did not produce any change in them. Okay, now there are some parts here that I want to just kind of note to you. First part that I want to note is what we mean when we use this term null. Null means zero. And so the reason why they're saying that there's this null or this zero hypothesis is that we're saying that if we look at the mean scores of the group, right here I'm saying pre and post. What I mean by this is we're saying we have a mean score of what the group was telling us before they got their treatment, and post means after. So we're saying that we also have a mean score for what the group was saying after their treatment. If we get a result that looks like this, then what we're saying here is that the mean score of the group after treatment was equal to their mean score before treatment, or there was no change, right? So going back to our example, the researcher measured the level of depression in the participants before they got the medication. Then the researcher measured the level of depression after the medication. And what we're seeing here is that there's no change from before to after. What does that mean? It means whatever we did to our participants, it was not effective. Okay, so this is one prediction, one hypothesis that the researcher has to acknowledge is possible. They might not get an effect. So that's one prediction that the researcher is going to make. We could say that it's the not desired prediction, right? The researcher doesn't want to find this. They don't want to find that the thing that they did to their participants was not effective, but it is a potential outcome of the study. And so that's what they're doing here is they're just laying out what are the potential outcomes. So the first potential outcome is the null hypothesis, which says that no effect happened as a result of the IV. And the way that we know that is because their mean score of the participants before the treatment was equal to the mean score of the participants after the treatment. So there was no change here. Okay, so that's the null hypothesis. In this step one, the researcher is also going to make another prediction, or they're going to state another hypothesis. The other hypothesis that they're going to state is referred to as the alternative hypothesis, right? So it's saying if the null doesn't happen, then this alternative outcome will happen instead. This alternative hypothesis is often referred to as H sub 1. I forgot if I noted what this one is called. For short, we often refer to the null hypothesis as H sub O. And we refer to the alternative hypothesis as H sub 1. What does H sub 1 say? It says that the IV is effective. And how is the researcher going to be able to determine this? Well, they're going to take that mean score before the treatment, compare it to the mean score after the treatment, and they're going to find that the two scores do not equal each other. So there has to have been a change, right? So whatever score happened here is different from the score that happened here. Therefore, some change must have happened, and we're going to attribute that change to the independent variable. Okay, so in terms of desire, we could say that H1 is the outcome that is desired by the researcher. Okay, so treatment is not effective with HO. Treatment is effective with H1. We're saying that then is our step one in the experiment in the hypothesis testing that we are doing. Okay, so from there then, what is step two? Step two is where we're going to take a moment and we're going to locate what we refer to as the critical region. Let me go ahead and note what I mean by the critical region. Here I'm saying it's the extreme 5% of a null distribution. And I've got a curve here that's showing this. Okay, so here we're saying that this is a curve, right, a histogram, showing the results if HO is true, right, if the independent variable was not effective. In the middle of this curve, we have our mean, and on the two ends, we've got these two tails that we've identified. And the two tails boundaries are being denoted by these two z-scores, a negative 1.96 and a positive 1.96. What are these two z-scores doing here? Well, we're saying that that is where the extreme 5% of the distribution is, right? So remember from like chapter 7, we were doing problems where we were figuring out the different percents of the curve. The reason why we were doing that was so that we can apply that knowledge here now. Okay, so what we're saying here is later, after step 2 is finished, I'll just kind of cut to the chase. We are going to move on to a step 3. Right, and step 3 is where we're going to collect our data and we're going to compute 2 statistical tests. Those 2 statistical tests are going to be conducted using 2 different operational formulas. Luckily, we've already been learning those 2 formulas for the past couple of chapters. The first one is standard error. Right, so remember, this was the new kind of standard deviation that we are calculating when we are pulling out different samples from a population. Here, I want you to notice that the symbol for standard error is remaining the same, and the formula is as well. It's still the standard deviation divided by the square root of n. In addition to that, we're also going to calculate our z's. Remember that beginning, I think it was in chapter 6, that when we calculate z now, we calculate it with our denominator being occupied by our standard error, right? Before it used to be the standard deviation that would go here. Now it's this new type of standard deviation that's going to go here. Okay, so when we complete step 3, we will have ended up with some particular z-score. This has to do with what we're talking about in step 2. Basically, what we're saying in step 2 is once we've calculated our z-score, we're going to use it to determine whether our treatment was effective or not effective. The way it's going to work is if the z-score is in this region, right? So remember, when we're talking about this 0 here, we're saying that right under the mean is 0. So we're saying if the z-score is anywhere in this region, let's say if the z-score is here or here, right, within the boundaries of the two 1.96s, then we're saying that there was no effect. Another way that you can kind of note that is if there's no effect, then the z-score that we calculate is going to be smaller than 1.96 going this way and smaller going this way. Why is that the case? Because if the z-score is any one of these units, it's going to be closer to 0 and it's going to be less than the 1.96. Okay, and when I say 1.96, I'm saying like the absolute value, right? So it would be like 0 or like 1 or something like that. Okay. However, on the other hand, if we go through step 3 and we find a z-score that is in this region or in this region, then we're going to say that there is an effect, right? So if z score is here or if z score is there, then there's going to be an effect. Okay, so maybe one thing that we should note with that is, I'll note it here. If z is smaller than that 1.96, then we're saying there's no effect. Our independent variable did not cause a change in the participant's behavior in the way that we predicted. That's what would happen if this score that we calculate is smaller than the 1.96. However, if on the other hand, if z is greater, then, right, if it's greater, say if like I get a z-score and I find that that z-score is like 2.03, right? 2.03 is bigger, it's greater than 1.96. From now, I would conclude that there is an effect. Okay, so let's just make sure that you're following everything I've said so far. Step 1 is that you are going to state your predictions, your hypotheses. You're going to state your null hypothesis, your HO, which is your prediction that your independent variable is not going to work. You're also going to state your alternative hypothesis, your H sub 1, which is your prediction that your independent variable is going to work, is effective. Your step 2 is where you're going to identify the critical region, right? And the critical region is kind of like saying how you're going to state how high the z-score has to be if you were going to say that it had some effect. Here we're saying that it's got to be greater than that 1.96. And I'm using the 1.96 because in most studies that are conducted, this is the cutoff region where the researchers will say, okay, if the z that you calculate is smaller, then no effect. If it's bigger, then effect. Okay, but then that we follow step 2 by going ahead and coming straight into step 3, where we collect the data and we conduct our 2 calculations. Remember that the only reason why you're calculating the standard error is because you're going to use that as your denominator in your z formula. But once you're done with that, we're saying that then you move on to step 4. Step 4 is where we say you make your decision. Right? The decision is, which hypothesis was correct. Was my treatment effective or was my treatment not effective? And we're going to make that determination based on exactly everything that I've just said about the critical region. For instance, let's say that we get this outcome. The obtained score is in the critical region. Now remember, by critical region, what I mean is that the critical region is either of those boundaries that we're talking about, right? So the critical region could be inside of this tail or inside of this tail. In either case, if your Z is here or if it's here, that means that your Z is greater than this 1.96. In that situation, you reject HO. Right? When you reject HO, you're rejecting the statement that says that your treatment is not effective. And you're also saying, it's unlikely that I get this sample mean if the null were true. Okay, so maybe another way that you can say that you're making your decision here is that in this situation, where Z is greater than 1.96, and you reject HO, my decision is that the IV is effective. Okay, I rejected the null hypothesis. I rejected the statement saying that the IV was not effective, and my decision is that the IV is effective. Okay, so then let's look at the other decision that we'd have to make. Alternatively, if the obtained score is not in the critical region, if it's less than 1.96, then we would accept the null hypothesis, right? And so remember here now what we're saying is we've got our data, we identified our critical regions, and what we found was that our Z was somewhere in the middle, right? It was less than the 1.96. So we're saying I'm going to accept the null hypothesis. I'm going to accept HO. So here what we're saying is that the decision that I've made is that based on the data, the IV is not effective. And the reason we're saying that is because with this outcome, it's likely that I'd get this sample mean if the null were true. If the null is true, the IV is not effective. Okay, so that is the four-step process that you're going to be running through in the problems in the textbook, both the evens and the odds. And so I just want to kind of highlight that. So the first step is you're going to state your two hypotheses. Second step is you're going to identify your critical region. Third step is you're going to collect the data and compute your two test statistics. And so then the fourth step is you're going to make your decision. Okay, my cat is needing some warmth here, so I'm going to bend over and give her a little blanket action. Okay, kitty. Okay, so sorry for that distraction. So we've just gone over the 4 steps of the hypothesis testing procedure. Now I just kind of want to add a couple of other details. First detail I want to add is with regard to this decision that you've just made, right? So you've just decided either your treatment was effective, the independent variable was effective, or the independent variable was not effective. We say that when you make this decision, it is possible to make an error in that decision, right? So let me just kind of note that that's what we're talking about. We'll say errors in the decision. It's possible that can happen. So I want to take a look at what would the different situations look like if you did make an error, and what would these errors be called? To describe this, I want to just kind of begin by noting that I've laid out like a matrix that's showing first the potential outcomes of the study, right? So you've just conducted this experiment, and in finishing the experiment, you are going to get an actual outcome. You're going to get an actual result of the study, right? And here are the only two potential outcomes that are possible. One potential outcome that's possible is that you conducted the study and you found that the null hypothesis is true. Now remember, based on what we were just saying, if you find that the null hypothesis is true, what you have found is that there was no effect. And that was your outcome of the study, right? Because remember, null is the operative word here. Null means zero. So if null is true, there's no effect of the independent variable on the dependent variable. However, the other potential outcome that's possible is that the null hypothesis is false. Here we're saying that you conducted your experiment and the actual outcome that you received is that there is an effect. We'll say yes, effect. Okay, so first part of this decision matrix is saying, here's your potential outcomes. Either you found no effect of your independent variable, or you did find an effect of your independent variable. The other part of this matrix is this over here, the actual decision that you make, right? So when you go to make your decision, based on what you see from the data, your understanding of the data, you're going to decide to either reject the null hypothesis, right? And if you do this, if you reject null, then your decision is that you're saying that yes, there is an effect. I rejected the null, I rejected the zero, and I said there is a difference between the groups, therefore I had some kind of an effect on my participants. However, the other kind of decision that's possible is you accept the null hypothesis. Remember, if you accept it, you're saying, yeah, I did not see an effect. Okay, so now here is where we're talking about how you can make errors in decisions. You can reject the null. You can say that there was an effect when in actuality there was no effect, right? So we'd say there's like a box right here, and that box would occupy this mistake that you've just made. And so let's look at how that box looks. Here, we refer to that mistake as a type 1 error. What is this type 1 error? The error that you've made is that you said your treatment was effective when in truth it actually was not effective. Okay? Let's look at what would happen in this box. Right here we're saying, here I've decided to reject null. I've said, I think that I did find an effect. And then here we're saying, and yeah, the actual outcome is that there is an effect. So he would say then that there is no error. You decided that your treatment was effective when it actually was effective. So there's no error in that quadrant. However, let's look at the other kind of mistake that a researcher could make. The other kind of mistake that they could make would be found in this box here, right? And it's referred to as a type 2 error. Here we're saying the actual outcome was that your treatment was effective. It did produce a change in your participants' behavior, but you missed it and you decided that there was no effect. Right, so it's a false no effect. False no effect in that you thought it was not effective when actually it was. Now, one thing you might want to think about is which of these two types of errors might be more important to be aware of? Some researchers would argue that the type 1 error is the one to really be aware of, right? Because think about the mistake that you're making here. Your treatment was not effective, but you say it is. And then you proceed as if it is. Maybe we're talking about these antidepressant drugs that you've just tested. You thought the drugs worked when they actually did not work. And so now, because you think that they work, you're going to mass produce them and you're going to give them to patients. And it's not going to have any effect on their levels of depression, right? Think about how many people will be underserved or misserved in that scenario. Okay, so just to make sure that you guys are understanding how we're talking about these two different kinds of errors, we're saying that what's happened here is, so to start off with, you decided, right? If you make an error, you have decided that either the treatment was effective or it was not effective, when actually it was either not effective or was effective. Let's also just note that if I make a decision and my decision falls in this quadrant, it's also another situation where I did not make a mistake, right? Because I accepted my null. I said there was no effect. In the situation where the null was true, there actually was no effect. So no error in that case. But from there's a couple of other things that we want to talk about with regard to inferential statistics. The next one is tails. Right, so for the past couple of chapters, I've been referring to these histograms that we draw that I've been referring to as curves, and then we've been saying that we've been drawing tails on the ends of those curves. One thing I want to point out now is that when we do this, we can say that we can conduct a study, an experiment. It's either a one-tailed test or a two-tailed test. And so I just want to describe what is the difference between these two types of tests. First, let's note each of these is a situation where we're conducting an experiment. And each of these has to do with the prediction that you're making. So let's say that if I conduct a study and I use a one-tailed test, when I made my prediction, right, that step 2, I predicted that if the scores were going to change, if my treatment was effective, my scores would either go up or they would go down. But I'm predicting what's going to happen. Okay, so let's say, for instance, an example is this. I predict that the meds will lower depression. What I've just done here was when I made my prediction, I predicted what direction the effect was going to go in. I said the medication is going to lower depression. So let's think about what that means in terms of the curve that we're going to draw. Right, so we said we're looking to see if we calculate a z-score, and if the z that we calculate is in a tail or if it's in the middle. Oh, actually, let me redraw this. In this prediction, I did not make this kind of prediction. Instead, the prediction that I just made was this. I predicted that the z-score that I'm going to get should be here, right? And the reason why I'm saying that is I just predicted that the meds will lower depression. So I'm going to go and I'm going to measure the level of depression in my participants after they got the medication. I should find, if the medication was effective, that the majority of their scores is here, right? It's low relative to the mean. So this is an example of a one-tailed test because I'm predicting where the z should be. Okay, So now and you could do this where you're predicting that maybe the Z is going to be over here, right? It's going to be higher than the mean. Thing that we're just saying though is when you conduct a one-tailed test, you're predicting that your Z is going to be on one side of your curve. Either it's going to be lower than the mean, or you're predicting that the score is going to be higher than the mean. And you are saying, I know where it's going to be. I know which direction the data should go. For instance, the meds should lower the depression. Okay, so then let's compare that to a two-tailed test. A two-tailed test is where you would make a prediction, and what you're saying is, I think that my independent variable is going to cause a change in behavior, but I don't know what that change is going to be. So let's say, for example, here, what we could say, if we're talking about the meds, is I predict depression will change, right? So I'm starting off, if I'm making a two-tailed test prediction, I'm starting off saying, but here's what's going to happen if my independent variable is effective. The level of depression of the individual is going to change. But I don't know if depression will increase or decrease. Right? I don't know what the medication is going to do to my participants. Maybe I just made the medication and I'm testing it for the first time, so we just have to see what is it going to do to our participants. If that's the case, then when we go to draw our curve, that's a situation where we're saying that Z-score that we calculate in step 3, right, and we compare it to our critical region, that Z could be here. Maybe the meds cause the depression to go down, or the effect could be over here. The meds cause the depression to go up. We don't know. So we're saying that we're going to identify both regions as potential outcomes, right? Two-tailed test because there's a tail here and a tail there. Up here it's a one-tailed test because we're predicting where that change is going to occur. Okay, so I'll also, note that I think in the book, when we go over the problems, most of our tests are going to be two-tailed tests, right? And so you can kind of see, okay, how is the researcher not seeing the direction of change if it's a two-tailed test, and the problems that we'll go over. But the next thing I want to talk about is effect size, right? So what we're saying here is effect size is this measure of the effect of the independent variable. Here we can note it in this kind of formula where we're saying that we have measured these two means. We measured the mean score of the group before the treatment, and we've also measured the mean score of the group after the treatment, right? So this could be that level of depression. We'll call it depression level. They had that level of depression before the treatment occurred that we measured. Then we gave them pills, and there's that level of depression after the treatment. If there's a difference, right, if there's a change, then whatever the difference here is going to be something other than 0. It's going to be some number. And we want to know, okay, well, what number is that? Would that difference be a 1? Would it be a 5? Would it be a 10? Would it be a 20? Would it be 100? Right, because think about the how large the number is. However large the number is telling you how effective your treatment was. Okay, so one way that we have of measuring effect size is this other measure called Cohen's d. Right, Cohen's d is just simply like this other statistical measure where we're getting some sense of how big the difference was between before the treatment and after the treatment. How do we measure this? We say that it's a division problem where in the numerator you've got that before mean, and you are subtracting it from your after mean, and that's divided by your standard deviation in your group. Okay, so one last thing that I wanted to talk about is something referred to as power. And here I'm defining it as the probability that the test will reject the null. Okay, so if it's the probability that the test will reject the null, what we're saying power is power is something that you are going to assess before you even conduct your experiment, right? So it's the probability that I will reject the null. If I'm rejecting the null, then I'm saying that my treatment was effective. So power is a measure of how likely it is that you're going to be successful in your experiment. Your independent variable is actually going to have some effect. Now, what we want to just note here is if you're a researcher conducting a study, this is what you want. You want to reject the null. You want to be able to say your independent variable was effective. If you have this tool where you can measure it, right, how likely it is that you'll reject the null, then that tool will help you construct the experiment so that you are successful in this endeavor. And so here I just want to talk about 3 different ways that you can construct the experiment to help you increase the probability that you'll find an effect in your study. Right, so we're saying ways to increase power, ways to increase the probability that I'll reject the null, ways to increase the probability that my experiment independent variable will be effective. The first way to do this is to increase alpha. Oh, I don't think I talked about alpha. Alpha is what we refer to, we're talking about that thing that we're referring to as the critical region. Right, we say here, I want alpha to be where there's this, if my z is effective, it's going to be in 5% of the distribution, either, right? So this is like a 95% here. So we have 5% on the 2 ends over here. We split that 5% up, 2.5% here, 2.5% there. We note that we're looking in this 5% of the tail by referring to it as this new Greek letter that we can talk about called alpha. And we say alpha is set out here at 0.05. What does alpha equal 0.05 mean? It means that we're going to look in the extreme 5% of the distribution. We're either going to look in this tail or in that tail. Okay, so here we're saying a way that you can increase the probability that you'll find effective independent variable is to increase alpha, right? And that increases power. I guess a way that you can think about that is to think about these 2 curves stacked on top of each other, right? So let's say this is the curve here where you said your alpha was 0.05. So this is that curve that we have on the other page where the 2 z's are the 1.96. And we're saying that the result is that the independent variable is effective if I have a z in this region or a z in that region. A way that you can do this is you can say, I'm going to increase alpha. I'm going to make it bigger. Let's say I make it, instead of 0.05, I make it 0.10. Right, so I've made alpha bigger. What have I done when I've done that? I have increased how much critical region I have in my study. Now I've said, here's the region that the z can fall in and that z be effective. Right, so I've made my critical region bigger. I've made it so it's easier to find a Z in the critical region than in the 0.05. Okay, so that's our way of increasing alpha, and then that leads to increased power. Second way that you can increase power is that you can conduct a one-tailed test as opposed to a two-tailed test, right? If you can say, oh, I know that my Z is going to be in that tail, then you're making a more specific statement. If you're making a more specific statement, it's easier to find that outcome. Okay, so then there's a third way that you can do this. You can just recruit more participants, right? The more participants that you recruit, the more likely it is that you will have a significant effect, that you will reject your null, your independent variable will be effective. Okay, thank you very much. That's it for the video lecture on the textbook. I look forward to seeing you in the odds problems.